I have to start with exponential rules, but I'll be really quick. So we have exponential rules, which are number one, a to the m times a to the n is a to the m plus n. Now, why is this true? Well, some people say that, oh, it's because you have to add, and that's not the reason, because that you're just simply reading off what this rule is saying, right? The reason that this is true is because if you have, say, times a cubed, this is same as a times a. That's what square means. You're multiplying a twice, right? And a cubed means a is multiplied by itself 3 times. Now count how many times you multiplied a. You multiplied it 5 times, right? And then only after this, you look at what happened. Oh, I end up adding the exponents. So that's why this is true, okay? Number 2, if you divide, in this case, it's going to be subtracted. And again, you can make the same argument. Suppose you have a to the 5th power over a squared, then it's a times a times a times a times a divided by a times a, and you can cancel out the same factors, which allows you to say this is a cubed, but then look what happened. You've subtracted, right? Number 3, a to the m to the nth power is same as a to the m times n. And that's like, example is, say you have a squared to the 3rd power. That's like a times a times a times a times a times a. So this is a to the 6th power. And a quick way to explain why you end up multiplying these is like, if you have 3 bags of candies and each bag has 2 candies, how many candies do you have? 2 times 3, that's how you count them, right? Yeah. So that's why you multiply. So of course you have to multiply. So that's why this rule is true. Number 4, anything to the 0th power is 1, and the reason for that is just from this one. If you have a squared over a squared, according to this rule, what is it? That's a 2 minus 2, which is a to the 0th power, but anything divided by itself is 1. So anything to the 0th power is 1. Good? Right? Next, a to the negative nth power is same as 1 over a to the mth power. And the simple proof is that if you have a to the negative m, that's same as a to the 0 minus m. But now you use this rule backwards. If it's 0 minus m, that's a to the 0th power over a to the n, right? So you can write down a to the 0th power over a to the nth power. But what is a to the 0th power? 1. We just see that it's always 1, so it's 1 over a to the nth power. Okay, and then finally, there's a to the 1 over nth power. This is same as mth root of a. And the rationale is that if you take a to the 1 over m and take it to the nth power, that's a to the 1 over m times m because of this rule that we just proved. So they cancel and you get a to the 1st power, which is just 1, which is just a, right? A to the 1st power is just a. And look at what this is saying. This is the definition of mth root of a, right? That's a bit cryptic. Let me try to explain this a little bit more. What is cube root of a? This is some number. This is some unknown number whose 3rd power is equal to a, right? And if you think about a to the 1 over 3rd power, then just by this calculation, you know this is a, so these two must be the same. They satisfy the same thing. Okay? So that's the argument. So these are the basic exponential rules. And what this allows you to do is, although initially mth power means you're multiplying a m times, which only will allow you to have these m and n's to be positive integers, you can extend the meaning of exponents by these additional rules. you're really extending the exponential rules so that you can put 0 on the exponent, you can put negative numbers in the exponent, you can also put fractions in the exponent. Okay? And you can go even further. You can put any real number in the exponent just by some limited process. So that allows you to define what's called the exponential function. So here's an example of an exponential function. Okay. And let's try to graph this, see how it looks like. Make a chart, x, y. Value of this function will be y. So if you put -2, -1, 0, 1, and 2, what is 2 to the -2 power? We just reviewed it. This is equal to what? 1 over 2 squared, which is 4, yes. So this will be 1/4. 2 to the -1 is 1 over 2, which is 0.5. Well, it's 1 over 2. Or 1 over 2 to the first power. Just using the rule that I just erased. What's 2 to the 0th power? 1. Anything to the 0th power is 1. 2 to the first power is, of course, itself. 2 to the second power it would be 4. Okay. So once you make these tables, you can plot it. At 0, it's 1. At 1, oh, I need say this is 1, here's 2, this is 2, 3, and then 4. So at 0 it's 1, at 1 it's 2, at 2 is 4, at -1 it's 1/2, and -2 it's 1/4. And now you connect these dots to form a smooth graph, and that's the graph of this function. Okay. If you taught a child who just learned multiplication, that 2 to the 3rd power means 2 times 2 times 2, and try to show this, it won't make sense to that child because they would only understand it as multiplying something by some number of times. But what we've done is we've extended the meaning of the exponent so that not only you know how to take 0th power, but you can also do 1/2 power or 1/4 power. So all of these numbers in the between also make sense. So you get a continuous graph. Okay? So that's an exponential function. But then I promised that we're going to do logarithms, and this is where the logs come in. Anytime you have a function, you can define something called an inverse function. Is that right? What is an inverse function? Does anyone remember? Yes? But what kind of opposite? So one common mistake is people think inverse means you take the fraction and you flip upside down. Well, that's the multiplicative inverse, but that's not the inverse of as a function. Yes?
Like if you look at it on a graph, it's like perpendicular.
No, that's not right. Yes?
You swap X and Y.
That's correct. You swap the input and output, and what it does to the graph is that here's X, here's Y. If you swap this around, that's like rotating the graph along the y equals x axis. So what happens is that this graph that was here, if you flip this over there, so just draw this really carefully on a piece of paper, and if you fold along this as your crease, you'll see that this one will have a graph that's like here. Okay? That's the graph which we call the log. Okay? So I'm trying to introduce the log now, and what log is. So there's something called the log 2 of x, and this is the inverse function of the function that we just defined. Okay? But this process of switching input and output is very confusing, so often I try to use the following image. So if you can try to imagine with me this concept of inverse function would be not so hard. So think about this. What's a function? Function is like a factory, right? You put something in, something comes out. You have an input and you have an output. It's like a factory, but it has to be consistent, meaning that if you plug in 1 and you got a 2, then 1 should always give you 2. If you put 1 and you get a 3 the next time, that's not a function. Okay? Function should always give you the same output for the given input. Okay? So, but function is like a factory. Okay? So imagine some kind of a factory where you put in chickens, and out comes chicken nuggets. Nice function. Okay? A function that takes chickens and gives you chicken nuggets. Okay? Now think about what the inverse function of this is. What would the inverse function do? Yeah? Yes, exactly. So the inverse function would take in chicken nuggets and it will give you back real live chickens. Of course, this is scientifically impossible with our current technology, but just imagine that. That's our inverse function, okay? So if this is the function where it takes the number and gives you some output, the inverse function is like the opposite, where you take the chicken nuggets, gives you chickens back. Now, the reason I'm trying to give you this imagery is because it's very important to know what happens if you compose the two functions. So often, when you plug in one function into another, that's called the function composition. And it's written like this, but that's not so easy to understand. What does this small circle mean? This circle means this, okay? So you want to know what happens if you take the output of one function and give it to the next function, okay? So imagine this situation. Let's do this one first. Fx, f inverse. Okay. So this one's like, f is the chicken nugget factory, right? You put in a chicken, you get the chicken nuggets. But then you put it into inverse function. What do you get now? Oh, you don't get it? You have initially you put in a chicken, the first function does what? It gives you chicken nuggets, okay? But you take that immediately and put it into the next inverse factory, which gives you back chickens. Okay. So whatever you start with, the two things will just undo each other, and you're going to get what? X. Okay. All right. And you can also do the other one where you start with the chicken nugget, and out comes a real live chicken, and you take that chicken and put it into the factory again. What do you get?
Chicken nuggets.
Chicken nuggets, right? So you started with chicken nuggets, you came back to the original chicken nuggets you had, right? So this will again be x. Now, these two relations are fundamental to being an inverse function. So this is a bit outside the curriculum, so I can't really prove it, but this is what happens in general. This happens in general. If you're given a function, and if f of g of x gives you x, and g of f of x gives you x as well, if both of them give you x, then any function g satisfying these two relations is the inverse function of f. Okay? So we observe that if g of x is an inverse function, then it will satisfy these two relations, right? Because what inverse functions basically undoes, it's like a control z operation. You know? It just, whatever that it did, they kind of cancel each other. And so you get back the original one. Okay? But if they can cancel each other in two different orders, then it means, okay? And that's a bit outside of the scope of this class. If you choose a math major, then you'll learn this in the proof class, some basic proof class. Okay. All right, but what I'm going to do is this is not the usual way that you're taught logs, but I find it to be the most convenient way to explain all the log rules. Okay. In our these two things mean that if you compose these two functions in any order, two things cancel out and you get back the original x. Make sense? Okay, so let's see what that means. It means if you have two, let me do this slowly. So let's say we first want to do f of f inverse of x. What is this? Well, first of all, I'm going to copy f. What is f? F is whatever you put in here is 2 to something. Do you agree? Okay, that's what it is. And then I'm going to plug in f inverse of x over here, which means what should I write over here? F inverse of x. You have to plug in the same thing, right? Is that okay? But what is f inverse of x? Log base 2x. So this is going to be log base 2 to the log base 2x. Is that okay? That's what this is. Okay. And what is this supposed to give you? X. So this must equal to x. If these two are truly inverses of each other, that's basically the definition of what a log is, right? Being inverses means that they cancel and you just get back your x. That's what it means, right? Now let's try the other one. F inverse of f of x. What does that mean? Well, think of it this way. You first copy down what f inverse of x is. F inverse of x is log of 2 of x, right? Log 2 of this. So whatever you plug in here, because that's what x is, you're going to put it in here. What do I want to write here? F of x. So, which is 2 to the x, right? So I'm going to put this here, which means that this is what you put, but f of x is 2 to the x, so it's log 2 of x equal to x, which cancels. Okay, I do agree that that was a bit cryptic, but at the end of the day, this is the only rule that you have to know, which is that in general, and this will be our fundamental starting point, okay? So in general, if you have a to the log base a of x, these two are going to cancel. These two are going to cancel, and you are going to get x. And also, if they are composed in the opposite order, log a of x, these two are going to cancel, and you're going to get x. These two rules is equivalent to saying that log a of x is inverse function of a to the x. So here's the big trouble with logs. Conceptually, inverse functions are hard to understand. And most textbooks start off by saying, what is log? It's an inverse function. Oh, that's so hard. Okay? And that's why you get confused. And you're already lost in the first week. And then at some point, the week passes and 2 weeks go by, you still don't understand what you're doing. And that's over. The class is over. And you never learn logs. That's what happens to some of you. Okay? But we're going to try to avoid it by saying, instead of saying that it's inverse, there's an equivalent statement, which is that logs are anything that cancels with the exponential functions these two ways. So if you know how to do these two calculations, it's the same as this one. You don't even have to worry about being inverses. Is that good? That's mentally less challenging. Would you agree? Okay, so now we're ready to understand everything that you were taught about logs. So let's start some examples. So first of all, what is log 2 of 4? Well, we're going to use this. So you're going to rewrite 4 as 2 to some power. 4 is 2 to what power? Second power. And now how does it work? Cancels. I get 2. Done, right? Okay. Here's another one. Log 2 of 32. This is a bit bigger. What is it? 32 is 2 to what power? Fifth power, yes, very good. Okay, you cancel and it's 5, done. Now, here's my claim. If you know how to calculate it, you know it. Isn't that right? Yeah, if you know how to calculate it, you know it. So you know logs now. Okay? All right, a little bit more challenging. Log 2 of 1 over 8. What's that? Well, first, I know that 8 is 2 to what power? 2 to the third power, and somebody said it as well. This is the same as 2 to what power?
Negative third.
Negative 3 power. So what's the answer? Negative 3. You cancel it, you're done. See, you can calculate it so you know logs. Right. Okay, let's do another one. Square root. That's same as 2 to what power? 1/2 power. Square roots are same as 1/2 power. You learned that at some point, right? We did it. We did the reviews too. Square root is like square root, so that's like 1 over 2. So these cancel and you get 1/2. Okay. Right. Let's do something even harder. This might be a bit more challenging. What is log 2 of 1 over 2 times cube root of 2? All right, so that's the hardest one so far, and we have to take it slow. It's not so easy. So let's try this. First of all, this is 2 to the first power times 2 to the what power? 1/3 power, right? Now, what did we learn about multiplying two exponents?
Add them.
You add the exponents, right? If two things are in exponential form, the exponents add up. So this is going to be 1 over 2 to the 1 plus 1/4, that's 4/3. And then whenever you have 1 over something, what is that? That's
Negative 1.
negative. So it's 2 to the negative 4/3. And now you cancel. That's going to be equal to negative 4/3. Okay, that was hard, but we were able to do it. If you follow this calculation, then you pretty much can do any log calculations. So you already see that just knowing these two cancellation laws allows you to calculate logs. All right, so let me copy this cancellation law here because it's so important, but I need space. I'm going to erase it. Now let me prove some basic log rules. So, log rules. Oh, before I do that, there's another important one that I forgot. What is log 2 of 1?
0.
Why?
Because 2 to the 0 is 1.
Yes, 2 to the 0th power is 1. Okay. So the first one I want to write down is that. So log rules. Number 1, if you have log base anything of 1, it's going to give you 0. Okay?
You just said it was
Well, you just said 1.
Oh,
0.
sorry, that's 0. 0.
Okay.
Sorry. Okay. So anything log a of 1 is 0. Now comes the serious rules. If you have log base a of x times y, that's same as log base a of x plus log base a of y. I actually was really confused when I first saw this. It was like, all my life I was told multiplication and additions are different things. And now you're telling me they're the same. That here's a multiplication that's the same as addition. But then when I looked at this rule closely, I realized that that's not what this law is saying. It's saying that if you have a single log applied to a product, then that becomes 2 logs added. So the important thing is that you have one log and now you have two logs. That's why this rule works. If somebody writes log a of xy is same as log a of x plus y, this is wrong. Often this is the way people misunderstand it. Okay, but I'm going to do better. Not only I'm going to say that this is true, I'm going to prove this using the definition. As I said, these two are the only things that you need to know, right? So here's the proof. And I like to give this proof to make a point that this really makes these two rules allows you to prove anything that's in regards to logs. But also, when you see the proof, you see that all these log rules come from the exponential rules I initially explained, okay? So, I usually don't do any proofs, but this one I really like to show the proof. Initially, it must become really bad in order to become better. So I'm going to write down something horrible, but it will get better. Okay, so stay with me here. So what I'm going to first try is I'm going to rewrite x as a to the log a of x times, I'm going to rewrite y as a to the log a of y. Okay, what is that thing, you might ask? But it's really true, because if you simplify this, what do you get? How do you simplify this? You cancel a and log a. They cancel, they're inverse functions. What are you left with after cancellation? X. What do you get if you simplify this? Y. So I just decided to take this simple thing and make it look really crazy. Why would I do that? I would like to do it because now I can use the exponential rules. If you have two exponential forms, if you multiply, if they have the same base, what happens? The exponents add together. That's what we just learned. The same base, if you multiply, exponents add up. So that's what I'm going to write. I'm going to add them. Okay? Now what can you do? You can finish the proof now. How do you finish the proof? Look, what are we trying to prove? We're trying to prove that this is that, right? What do you do? Cancel. Done. Now you have log ax log ay. You sum it up. That's exactly what this is saying. So we proved it. Right? Okay. We only use this, right? And the log and the exponential rules. And in fact, if we didn't have the exponential rule, we wouldn't have this. And here's the thing, because log is the inverse function of the exponential function, every exponential rule that we wrote down in the beginning will have a corresponding log rule. Okay? So for example, we had the other one where if you divide two exponential forms with same base, then the exponents subtract, right? In fact, that's going to give us this next rule, which says if we divide x over y, then they subtract. Now, I'm not going to prove this because the proof is basically the same. But if you want to understand what we just did over here, I challenge you to do this after class. Try to prove this after class. It's exactly the same way. Okay. Number 4, log a of x to some power c All right. Okay. So one day I was reading my son a picture book, and it said, "The frog jumped over the log." And that was like a revelation. It's like, oh, this is it. This is how I should teach my students. So in the following semester, when I was teaching this again, I said, here's the rule, and I have a special name for it. And the name is frog over the log rule. So the picture book said the frog jumped over the log, right? So it rhymes, right? Frog over the log. And basically what I'm trying to say is that exponents inside the log, they behave like frogs. They jump over the log. And this is what you get, okay? Just have that picture image, and it just makes sense. And of course, even when I teach, sometimes I need to use this later in this course. Actually, I need to use this later in this course I have to use it. And it's hard to read this. So instead of reading it, I just say, oh, here we apply frog over the log, and everyone understands what I'm doing. So it's a nice way to call this rule, okay? All right. Now let's see this in action, see how this helps us. So here we struggled with this question, right? So we're going to take that and start applying these rules that we just learned, okay? So first of all, I see a division. What rule can we use? Division is subtracting between two logs. So I have log 2 of 1 minus log 2 of 2 times cube root of 2. Okay? Now, what's log 2 of 1? 0. We just learned that. Okay, so 0 minus, what is this? 2 times cube root of 2. Which rule do we use? This one, right? So we write addition. So we're going to put log 2 of 2 plus log 2 of cube root of 2. And we are almost there because, see, 2 is 2 to the first power, right? So minus log 2 of 2 to the first power minus log 2 of cube root is 2 to what power? 1/3 power, right? So you end up with, after you cancel, negative 1 minus 1/3, which is negative 4/3. Same answer, isn't that right? We got negative 4/3, same answer. The difference is over here we're using exponential rules. Over here we're using log rules. They are the same. You know, in those memes, the lady from The Office, this lady is shown 2 pictures, right? You see this one, and what's the difference? They're the same. Because they are the same rules. Exponential rules give you log rules. Okay, and apart from this one here, I basically made use of everything. I could even have moved this over here and then say this is 2 to the first power is 1/3 times 1. Yeah. Then I would have used everything. But this demonstration kind of shows you what's the convenience of having these. Now, lastly of the log rules, I want to discuss this last one, which is called the base change formula. Log A of B is log A of log C of B over log C of A. And this one is called the base change formula. And let me say a few things about this. First of all, this name, base change formula, is an official name. Don't go say frog over the log to other people because they don't call it by the same name. This is something I invented. They're not going to understand what you're saying. Okay? But the base change formula is an official name, and it's used everywhere. it's useful for calculating logs using a calculator. Let me try to explain what I mean. It does look a little cryptic, so let me first show you a demonstration, but then I'll show you a different reason why this is very useful. So first of all, if your question was log base 4 of 8, this becomes a bit challenging because it's like 8 is 4 to what power? You can't really say. 4 to the first power is 4, 4 squared is 16. It skips over the 8. It's not so straightforward. But you do see that 4 and 8 are both powers of 2. Isn't it right? So what you do is you say this is same as this, and I'm free to choose whatever the c is. And I choose c to be 2 because they are both powers of 2. Make sense? Yeah. So if I do that, if I write down log base 2 of 8 and log base 2 of 4, then suddenly everything makes sense. What is this? 8 is 2 to the third power, 4 is 2 to the second power. So if you simplify this, what do you get? The top. 3 over 2. Oh, because this is 2 to the third power, and then they cancel, so you get 3, right? 4 is 2 squared, and then they cancel. So base change formula allows you to settle cases like this, but it's the most practical formula because sometimes if you solve questions that deals with calculus and differential equations, often you end up with the answer that has logs involved. If you're taking a chemistry course, you probably have experienced that. There's some answers that come up with logarithms. And one of the problems is sometimes the answer comes out in the following form. Log base 2 of 3. Now this is even worse because at least 4 and 8, they're both powers of 2. That's not true for 2 and 3. There is no single number whose powers give you both 2 and 3. So what does this mean? Well, it means that this cannot be expressed in simple rational numbers. It will end up being something called an irrational number. You can't write it as a fraction of integers. But does that mean it's impossible to calculate? Well, you could by using a calculator, except your calculator, unless you have these expensive ones, if you have the simple scientific calculator, it's not going to have a way to enter log 2 of 3. Instead, your calculator will only have two kinds of logs. So there's the common log, and there's the natural log. Most scientific calculator will only give you these two kinds of logs. Now the big log with nothing under there, that this means it's log base 10 of x. Okay, and the big the ln is a shorthand for log base e of x. And e is what's known as the Euler's number. And it's about 2.7182818 something something. Okay, that's the approximate value. Yeah. This is another irrational number, so it doesn't repeat. You can't express it using decimals or fractions. Okay. Yeah, so there's a reason why people like this version of log of e, log. So although in practice, when it comes to engineering, people use log base 10. So for example, decibels, when you talk about decibels, a lot of times you use this one. But when it comes to calculus, there are some reasons I can't explain at this stage, but this will be the preferred one. The short answer is that if you differentiate this, you get some ugly function. If you differentiate this, you get 1 over x. I didn't even explain what differentiation is, but that happens. Okay. So, but what I'm trying to say, I kind of digressed a little bit. To come back to what I was trying to say is that you're only given these two logs, but no log base 2. So how are you going to express this using these other ones? Base change formula. You can choose this to be log base 10 of 3 over log base 10 of 2, just by choosing C as 10. Well, what does that mean? That is something that your calculator does have. You can rewrite this as log in your calculator, log in your calculator without anything there. And by punching this in, you can get the approximate value. Does anyone have a calculator? Can you give me the approximate value of this? But it doesn't stop there. You can also use C as E, this mysterious number E. So if you do that, you can rewrite this as log base E of 3 divided by log base E of 2, which gives you ln of 3, or capital ln of 3 divided by ln of 2. So I want some people to try this one, some people to try this one in your calculator. What do you get? Approximately 1 point what? 1.58? Okay, yeah. Approximately 1.58. In both cases, you're going to get the same answer because they're calculating the same thing. Okay? So that's the practical value of the base change formula. Often, you're going to solve some word problems, and your answer is going to come out in some log form. And if you wanted the approximate value, the only way you can do it is by going through the base change formula. Okay. All right. So that's it. I reviewed the entire logs in, 45 minutes, I think.